Welcome to part 2 of the XFdtd training series on the FICA Antenna Creation. In this tutorial we're going to go over circuit component creation and gridding and meshing. So the first thing you'll notice is that across the top we have our geometry tools. But in this pull down menu I can also choose component tools. Now these same tools can be accessed if I click on circuit components, right click, I can add a new circuit component with a feed definition, a passive load definition, a switch, a capacitor, or a diode definition, or no definition. When I'm using my circuit component tools, I can create a new circuit component with a passive load, feed, switch, nonlinear capacitor, and diode as well. And I also can create one with no definition. So I'm going to create a new feed definition. And what we're looking at here is the geometry location of our endpoints. Where I want to place my circuit is right about here on this feed leg, right between our PCB and this copper feed leg. If I know the absolute position, I can put in my X, Y, Z locations, or I can use our pick tool. So if I use our pick tool, I'm looking to get on the center of the lower edge here. I'm going to zoom in. And it's a little difficult to actually grab this lower edge. If you look at my pop-up tool, it's telling me that it's positioning it on the face. I can also press H to hide the part. So I want to get in the center of this lower edge, but this piece right here is getting in my way. So if I hit H, it hides the part, and then as I hover over this lower edge, I can easily grab the center of the edge. Now the tools in the middle I can actually copy from one location to the other. So in this case I have some fixed position out in space. And on endpoint 2 I have a center of the edge. I can copy from endpoint 2 to endpoint 1 so the 2 points are co-located. Now as soon as I do that, it's giving me a warning because I can't have my 2 endpoints co-located. What I want to do is add an offset between this point and this point. If I use the wrench tool, you can see I can just apply an offset in the X, Y, and Z location. You'll also notice that each endpoint is telling me that this is tied to the center of the edge, and endpoint 2 is also tied to the center of the edge. So this lets me know that I'm locked onto the center of the edge and not a face or an arbitrary point in space, so that if I would then move this location, it's going to stay attached to the center of this edge. I'm going to use our measurement tool on the right hand side to measure the distance from this edge to this lower edge. And one thing you'll notice is it's telling me the absolute distance between the 2 points I chose, which is 0.750635 millimeters, but it's actually telling me my X, Y, and Z distance. Looking at my global coordinate system in the lower left hand side, I know that this offset is in the Y direction, and in the Y direction it's exactly 0.75 millimeters. I'm going to switch back to our global select tool. From the pull down menu, I'm going to put in 0.75 millimeters. And you'll notice now the feed is going into the feed leg. One of the other options here is actually to swap the endpoint. So if I put this backwards, I can simply hit swap the endpoints and it would correct the direction of my circuit component. Let me swap it back. I do want my energy coming from my circuit board into my feed leg. Now I can click on Properties. In this location I can change the name from component to something like source or resistor or whatever my feed definition consists of. If I had multiple component definitions, I could choose them here. I could choose to include it in the mesh or exclude it from the mesh. I can choose if this component is a port or not, and therefore will it save port-related data. Under Advanced Options, I can also enable fixed points on endpoint 1 and fixed points on endpoint 2. We're going to talk about endpoints in a little bit, but for now just know that this is how you could choose endpoints to make sure that your source is lined up in a very specific location. I'm going to click Done, and I'm going to take a look at our component definition. So before, we did not have a circuit component definition, and we did not have a waveform definition. And you can also see that our waveform is an automatic waveform, and the automatic waveform is related to the 50 ohm voltage source. If I double click on our 50 ohm voltage source, this is where you would choose the properties of your feed. So in this case, we just want a 50 ohm resistor. We want a voltage source, not a current source. Our amplitude is 1 volt, and we're not going to add a phase shift or a time delay. One commonly asked question is why we have a phase shift and a time delay. And the reason for this is depends on what type of waveform you're using. So if you're using a sinusoid, it will apply your phase shift to that sinusoid, because a phase shift has a frequency domain property. A time delay is a time domain property, so when you're using a pulse, any waveforms that are pulse type waveforms will utilize a time domain field. Another common question is, if I'm trying to add a matching network, would I add the matching network here in the feed? And the answer is no. Adding the matching network here would sort of be like adding your matching network to the waveform generator. What you want to do in that instance is actually create a second component that has your matching network, your inductors or capacitors, and then attach that to the feed. The circuit component also has a waveform property. So I'm going to click Done. If I double click on Waveform, you can see that the type of waveform is actually automatic. The automatic is being set based on what appears in the project properties. So in this case, we requested a waveform from 500 megahertz to 2.25 gigahertz. I'm going to click Done. So we have about that frequency domain content. I can override this selection and choose something like a broadband, a Gaussian derivative, modulated Gaussian, or sinusoid. There's also a user-defined file type if you have a particular waveform that you're trying to enter into the system. If I go back into my project properties and I modify our minimum maximum range, so it's 500 megahertz to 500 megahertz, I'll click Apply. You'll see that the type of automatic waveform actually updated to a frequency domain sinusoid. I'm going to change this back to 2.25 gigahertz. Click Done, and we're back to our time domain pulse. I'm going to click Done again. Now that we've placed our circuit component, we're going to look at the grid. Right now we're looking at the target cell size and the estimated problem size. So if our entire grid was made up of 1 millimeter cells, it's going to take around 100 megabytes to run this project. When calculating the base cell size, one of the rules of thumbs you want to use is you want around 1/10 of a wavelength of padding at the lowest frequency. In our case, that's 500 megahertz. So the cell size should be around 3 millimeters. Some other options in here, if you go to Advanced, you can actually set the base cell size in the X, Y, or Z directions independently. You can also change the padding independently. One common instance where you want to change the padding is if you're running something over a PEC ground plane. In that case, you want to remove the padding between your antenna and the ground plane, which is going to be on your outer boundary. And you can do that in the lower Z direction and not affect the padding on the other sides of your antenna. We have options for global fixed points and global grid regions here, but actually each part can have its own fixed points and grid regions, and we find that a lot of people use those instead. They're a lot more straightforward to apply. So I'm going to click Done, and let's take a look at our grid. In this case, we have the option of mesh cut planes or 3D mesh. I'm going to keep the 3D mesh. You can see a little bit of this copper is actually poking through because right now we're actually viewing the mesh and reviewing our base geometry. So I'm going to come to the right hand side. I'm going to toggle off the parts visibility. So now this is just our mesh. One of the first things you'll notice is actually we don't see any copper on here. This is due to mesh priority. By default, XFdtd does not know which material should take precedence if you have overlapping parts. In our case, we have an antenna carrier, and right on top of that antenna carrier, we have our antenna. Because the mesh priority by default goes by the order of the project tree, it's assuming that the antenna carrier is more important than our antenna. There's a few different ways we can change this. I can actually move the antenna to the top of the parts tree, and therefore it would take precedence over our antenna carrier. Within each part, there's also a numerical mesh priority. So if I right-click on the part, gridding and meshing, mesh properties, there's a numerical priority value. By default, they're all set to 50. This is a relative number. So if I would bump this up to 51, it would take precedence over anything else with a priority of 50, regardless of the order that it finds in the tree. If I have two parts that are of priority 51, once again XF will default to the order in the parts list to break ties. I'm going to click Apply, and you can see that actually my slot antenna has now showed up. I'm going to change this back to 50 because there are several other ways that we can go about changing this. If I go to View, Parts List, this is actually a very compact display of what's going on in our project tree. What it's showing here is the absolute priority of our parts. It's giving us some information about grid regions, fixed points, the type of mesh, is the part visible, do we have locators on the part, and what material is the part. From here, once again, I can right-click, go down to gridding and meshing properties, or I can use what's called a macro. Within XF, we have a scripting engine on the back end. If you go to Help, Documentation, Scripting Documentation, you can learn more about our scripting engine. In this case, we also have a macros menu that's available, and that's a location for the scripts that you use a lot on a day-to-day basis. So on my parts tree, I can come down here and right-click, and I can import a script, or I can add that to my macros menu. So in order to set up the macros menu, we actually have a predefined one that we use for training. We're going to come down to Application Preferences, and in this window you will see that we have a default location for the macros menu. I'm going to browse, in this case it's a folder. I'm going to click Select Folder. I'm going to click OK. And now our macros menu is populated. In this case, I'm going to come down to Simulation, Set Mesh Priorities. What this macro is actually doing is going through and setting the mesh priorities based upon the conductivity of the different materials. Something with a high conductivity takes precedence over something with a low conductivity, and something that is lossy takes precedence over something that is lossless. So looking at our slot antenna, it's looking a little bit better. We now have at least our copper on the upper surface, but clearly our mesh is too big. You can also see that we can see through some of these faces. So by default, the face is chosen based on the material surrounding it. In this case, these faces are bordered by several different materials, and since XF doesn't know which one is the proper material to apply, it's going to default to seeing through the material. This would be a more accurate prediction of the Yee cell representation of the model. You can see it's actually a 3D representation of what's actually going to go into our simulation space. I'm going to flip back to edges only. So in order to refine the mesh further, we can actually set a local mesh size on each part. If I right-click on the part, gridding and meshing, gridding properties, you can see that I can set automatic grid regions and fixed points. A grid region is an area within your project that has a smaller cell size. A fixed point is a location in space where you're telling XF that you want an edge to go at this particular location. When you select fixed points on an object, it's going to look at the edges of the object, and it's going to try to determine locations where you need a cell edge to go across in order to have the geometry match up with your grid. In this case, I'm going to turn automatic grid regions on. If I go to advanced, you'll notice that I can actually set the automatic grid regions in the X, Y, and Z directions independently. In this case, I actually want to set them uniformly, so I'm going to go back to the basic mode. For my target cell size, I'm going to choose 0.5 millimeters. Done. Zooming in on our mesh, you can actually see that this is looking a lot better. But you'll notice there's actually 2 cells across our slot. Another rule of thumb we have is that if you have a slot or a trace, you usually want 3 to 5 cells across that gap. In some cases you want more than that, but a good rule of thumb to start with is at least 3. So I'm going to choose my antenna. I'm going to right click. I'm once again going to access the gridding properties. So in this case, I'm going to once again use automatic grid regions, but I'm going to set a smaller cell size of 0.3 millimeters. I'm actually going to set a boundary extension as well. A boundary extension extends this smaller cell size to a certain region outside of your part. So in this case, because we have our antenna, we actually want to extend that small cell size a little bit beyond the border of our antenna, just to ensure that the fields set themselves up properly. You can see that we have 3 cells across our slot, but we need to confirm that the geometry and the mesh instance of this slot match. So I'm going to come over here to all edges, and you can see that the copper edge is a little bit offset from our geometry instance. In order to fix that, we need to apply fixed points. So if I right click on the antenna once again, down to gridding and meshing, gridding properties, use automatic fixed points, done. The gridding engine remakes the grid to ensure that there's a cell edge directly at each of these edges in our slot. Going back to a larger view of our grid, I can actually switch to the mesh cut planes. I'm going to choose the XY plane. I'm actually viewing my antenna here because it's selected in my parts tree, but if I select something else, this is actually showing me the different layers of my mesh. And I can actually use this slider to step up through the mesh layers. If I zoom in to this location, another thing you'll notice that as I look at the mesh representation, it looks like there's two circuit components right here. What you're actually viewing is the geometry instance of the circuit component, which is the location we placed it on the mesh, and you're seeing the mesh representation of the component. So on the right hand side over here, I can actually toggle off components visibility, and that second instance will disappear. I can also view my mesh information. So if I click on View Mesh Information, over here we'll see the mesh edge, the grid position, the mouse position, and if I expand this just a little bit, we'll even see the material. So you can actually check edge by edge to ensure that this is my copper material, this is my FR4, over here I have my PCB, my PEC component lead, which is a continuation of my circuit component instance, and over top of here you can see that this is actually a source, it's a port, and it's of type feed. So this is a good way to go through and actually check your geometry and your mesh to ensure that everything you create in your geometry appears in the mesh before you do your simulations.